CVPR 2025, two paper discussions, both from Jiajun Wu. Jiajun Wu is at Stanford, and he works, I would say, generally what he's interested in is what kind of priors can we use to speed up AI, either to make it more data efficient or to make it more general, or both. So that's his key. The both papers they're kind of similar. There's also a presentation attached. So we have two papers in a presentation. One paper is product of experts for visual generation, and the other paper is Neuro-Symbolic concepts. And then we also have a presentation about Neuro-Symbolic concepts that he gave at Vanderbilt University. So overall, again, I usually don't like to mix up too many papers, but in this case, what's interesting is of course it's one author and the line that goes through. So let's start with product of experts. What he's trying to do here is when we have video generation, what we would like to do is we would have both a fidelity with physics and a fidelity with semantics. In other words, if we generate a video where rocks fall down from a mountain, we want the physics to be observed, and we also want the semantics to be observed. So the rock falls down and he rolls towards a house and then destroys the house. And we want this to be in some sort of physical reality. So the rock size and force kind of looks realistic. And then we also want semantics to be observed, so the rock actually hits the wall and doesn't go under the house or flies above the house or anything like that. So what this now means fundamentally is that we want to in this case they're using diffusion technology, so that is kind of a given, but within the sampling of the denoiser. So every time the denoiser comes up with a new suggestion for what they should be, for which element they should add to the diffusion process, there is also a physics and a semantic cost function included. In other words, we have information that the cost function, the optimizer, is exposed to, and therefore it has higher fidelity in physics and semantics. So this is the big picture explanation. I'm not, the purpose of this podcast series here is to give people a sense for what it feels like to run a hedge fund. So why do we even have these paper discussions, and what is the purpose? One purpose is certainly, here's what it's not. This is not a technical conversation. Don't use this podcast to learn actual technical details. We do put the links in the show notes. And there's definitely better sources for that. Most likely, you just want to go to the author's videos and presentations. What we're trying to do is try to explain to an audience of potential fund managers, but also interested people, how we link science, technology, and entrepreneurship together into wealth creation. And AI is the field that we're mostly interested in right now, because we believe that is the big wave of wealth creation, not just wealth creation, but probably also warfare and social change and all of these things, but certainly wealth creation. And these types of papers, like let's say this paper here, in our opinion, are crucial in the next wave of AI, which we call embodied AI. And within embodied AI, what we need is high fidelity video generation, so embodied agents can learn from video simulation, which is grounded in reality. And that's exactly what this paper is attempting to do by grounding video generation in physics and semantics. The other paper, which is Neuro-Symbolic concepts, this is something we also saw at ICRA. This is I would say, almost age-old question now, whether we need priors when we generate videos, or whether we can just do end-to-end. And I think Wu says that, look, if you have enough data, if you have good data, which is scale and diversity, you can probably train your model end-to-end with very little priors. You still have to have priors. We always have priors. Convolutional neural nets, they use priors, such as, for example, an assumption of symmetries, and when they break, then that is when, let's say, objects are detected or edges are detected. Transformers use priors such as self-attention, and they have a certain architecture, which is there is a prior. I mean, you have to have some assumptions of whether you're trying to optimize for, what you're trying to achieve with your model. But I think when AI researchers talk about priors, what they mean is more, what we don't want to do is tell the model upfront what to do, right? We want it to sort of organically learn from first principles or from data what it's seeing or how it's observing things. In this case, we're talking about video generation or image generation. And what we're trying to do is we're trying to have data efficiency, compositional, generalization, and continuous learning and zero-shot transfer. These are the four things that he's trying to achieve. In a nutshell, what he's trying to do is he's trying to create concepts. He calls it concepts. For example, objects like a dog or a human or a car. Those are objects, and they can be decomposed in some sort of feature space like fur, paws, and things like that. Actually, that can be learned. In fact, that can be learned. Whatever that feature space is that defines the object, that can be learned. Also, relational semantics can be learned. For example, left of, above, below, and then of action, which is put this cup left of the other cup, stuff like that. So all of these concepts can be decomposed into priors, and those priors can be used for generalization. So next time the model sees, for example, a dog that it has never seen in training data, it can use the decomposed features of what it means to be a dog and then infer that there's a dog there. And then also, that's the continuous learning part, immediately add this new observation into its latent space as a additional species of dog, for example. So fundamentally, I think what Wu is talking about here is, and that's why I picked this paper for discussion, it's the question of the bitter lesson. He is saying, look, the bitter lesson works if we have enough data. If we don't have enough data, we need data efficiency, and we just don't have enough data right now for most things. In fact, for almost anything, we don't have enough data. One thing we have, though, we have internet scale data for text and for coding, and that's why we're able to use ChatGPT for tasks such as code completion or homeworks in school and math and things like that. But this is, of course, only scratching the surface. When we start looking into embodied intelligence, there's a lot more than just understanding. Code completion is a really, really narrow task, and it's kind of like chess and playing Go, right? It's going to be solved because it's so narrow. But an Optimus robot flying to Mars and building the starbase up in Mars is a pretty complex situation, much more complex than playing chess or code completion. So therefore, we need some sort of generalization. We need something that can help us build robots that can first be trained on real physics without having to actually do it, and that will be the simulation, but then also that can generalize and do zero-shot transfer. And that's what Wu is trying to achieve. I think his work is very interesting. I think he is definitely, in my opinion, at the sort of crossroads of physics and AI, and that's really what embodied intelligence eventually will turn into. NVIDIA is working on this a lot. Just for new listeners, the papers we pick at CVPR are not based on some sort of our evaluation of the best paper. We don't have any academic ambitions here at all. What we look for is, we have two large positions in our portfolio, Tesla and Nvidia. We think that those companies are well positioned to drive embodied intelligence into the commercial space, and that is a big space, an important space, not just for commercial success, but also for things like defense, social aspects, healthcare, elderly care. So there's a lot of social implications of this, and global and economic implications. And it is our aim at Orange Capital Partners to invest in fundamentally new concepts and engineering practices with large impact. That's what we do, and this is definitely a big one. So, but in order to get there, we have to have a certain infrastructure, and the part of the infrastructure is, of course, the chips at NVIDIA, the algorithms, and the ideas such as this, where we think about what kind of priors could be used in order to speed up the training. Like, we don't need perfect, like, we're not, when we say, actually, we say that on our website, we're bitter lesson pilled, right? We are proud of that. What that means is that we do believe in generalization and scale, but we also have to acknowledge that there is clever ways to speed up things. You know, DeepSeek was a very good example. The parallelism that they introduce in test time scaling is very useful. And this is, in my opinion, a very similar approach, where we're trying to, maybe that's the wrong word, but we kind of cut corners, right? We say, look, instead of now learning over billions of iterations what it means when an apple falls from a tree, let's just sort of define an apple, a concept of apple, define the concept of falling, learn it at once, and then use the decomposed features of those concepts for general zero-shot transfer type learning in the future, so we can have continuous learning. I think that's the idea. So again, I think Wu is, in my opinion, a very interesting researcher. He's at Stanford now. I believe he also worked at MIT. So his approach is to try to sort of find a principled approach towards the real world. Are there things we can abstract away and use them as the basis, kind of like eigenvectors of things? Like, what does it mean to be a dog? What does it mean to be a tree? What does it mean to be left of something, or above something, or below something? What does it mean to roll towards something? And can we use those decomposed principles, or these decomposed components, and then compositionally put them together in a general, kind of like a Lego block type mechanism, and therefore learn new things on the go in zero-shot form. That's the idea, and I think it's very useful for robotics. It's also incredibly interesting for video generation, which again is really key for simulated learning. Thank you.